probability beyond the basics. We're going to discuss the complement of an event, the complement rule for probability, the addition rule for probability, the definition of odds, and the definition of a conditional probability. We're also going to talk about the complement of a set, the intersection of two sets, and the union of two sets, because set theory is the foundation of probability. Definition of the complement of an event. That is the list of outcomes that are not in the event but are still in the sample space. Things that are not in E but are in S, and the notation that's used to describe this list is not E. The complement rule for counting. N of E plus N of not E equals N of S. What this is the following. The number of outcomes that are in an event plus the number of outcomes that are not in the event equals the number of total possible outcomes in the sample space. Take a look at this picture. It's a Venn diagram. If we count the people in blue that are in region E, we'll see that there's 1, 2, 3, 4, 5, 6, 7 people. If we count the people that are not in region E, that are outside the region, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 people, and they're all in silver. By the complement rule, if we take the 7 people that are in E, we add them with the 13 people that are not in E, we find that it's equal to 20 people that are in this Venn diagram, the total number of people in this picture. The number of people that are in E, the number that are not in E, is the total. For example, consider the experiment of rolling a die. There are 6 possible outcomes when you roll a die, 1 through 6. The event of rolling a 5 corresponds to the outcome that is just the 5, and there is 1 outcome in that list, E. The complement of rolling a 5, or the complement of set E, are the outcomes 1, 2, 3, 4, and 6. They're all the outcomes that are not in E, but are still in the sample space. And there are 5 possible outcomes. Notice that 1 plus 5 is 6. If you consider the event of rolling a number that's less than 5, F has all the numbers or outcomes that are less than 5. 1, 2, 3, 4, because less than 5 means smaller than 5. Notice that there are 4 outcomes that are smaller than 5. The complement of F is a list of outcomes that are not in F, mainly the 5 and 6, but are still in the sample space. Notice that there are 2 outcomes in the complement of F. So that 4 plus 2 also is 6, the total in the sample. Consider the experiment of rolling a die again. The 6 outcomes in the sample space. If you look at the event labeled H, the event corresponding to rolling a number that's more than 5, more than means greater than, the only outcome that's greater than 5 in the sample space is 6. The complement of H are the list of outcomes that are not in H, 1, 2, 3, 4, 5, and there are 5 outcomes that are not in H, are in the complement. Notice again that 1 plus 5 equals 6, the total outcomes in the sample space. If you consider the event of rolling a number that is at least 5, at least 5 means 5 or more, so it is the 5 and the 6 that are listed in J. there are two outcomes that are at least 5. But the complement of J, the outcomes that are not in J, are the 1, 2, 3, and 4. And there are 4 outcomes that are not in J. So that 2 plus 4 is 6, the total in the sample space. If you consider, for example, having 2 children has a sample space that consists of 4 possible outcomes. If the event of having no boys is labeled E with the GG, notice there are no boys in that outcome. The complement of E is the BB, the GB, and the BG. Those outcomes are not in E, but they are still in the sample space. And notice that they are 3 outcomes. So 1 plus 3, again, notice is 4. The total number of possible outcomes. If you consider the event of having 1 boy, notice F is labeled BG and GB. Those are the only outcomes that correspond to having 1 boy. The complement of F is BB and GG. Those outcomes are not in F, but they are still in the sample space. And since there's 2 outcomes in F, this implies that there's 2 outcomes not in F, because there's a total of 4 possible outcomes in the sample space. Notice again, when you have 2 children, the sample space is the 4 possible outcomes associated with having 2 children. The event of having 2 boys is the one outcome that is BB. It's the only outcome that corresponds to having 2 boys. The complement of H, the list of outcomes that are not in H but are still in the sample space, is the GG, the GB, and the BG. There are 3 outcomes that are not in H. So 1 plus 3 again equals the total number of possible outcomes, n of s, which is 4. Notice the event of having at least 1 boy. The outcomes associated with having at least 1 boy is the BG, GB, and BB. Those outcomes, you have at least 1 boy, and there are 3. But the complement of J is a list of outcomes that are not in J but are still in S, namely the GG. And again, there's 1 possible outcome that's not in J. So 3 plus 1, once again, is 4. When you pick a card from a standard deck, the event of picking an ace, there are 4 aces in the deck. The complement of an ace is a non-ace, all the cards that are not aces. That means we remove all the aces. So this is a picture of a deck of cards with all the aces removed. And so if there's 52 cards in a deck, 4 of which are aces, that means that there are 48 non-aces. The event of picking a spade. There are 13 spades in a deck of cards. The ace of spades, the 2 of spades, up to the 10 of spades, the jack, the queen, and the king of spades. The complement of a spade is a non-spade. All the cards in a deck that are not spades. This is a picture of all the non-spades in a deck of cards. You got the hearts, you got the diamonds, and you got the clubs. Notice if there's 52 cards in a deck, 13 of which are spades, that means that there's 39 non-spades in a deck of cards. From a deck of cards again, if you consider the event picking an ace of spades, there is only 1 ace of spades in a deck of cards. If we think of the complement of an ace of spades, it's all the non-ace of spades. It's all the cards in the deck with the exception of the ace of spades. This is a picture of a deck of cards in which the ace of spades is excluded. So if there's 52 cards, one of which is an ace of spades, then there are 51 non-ace of spades. Consider the experiment of picking a marble from a bag. The lower left corner is a summary of what's in the bag. There's 1 blue marble, 2 red marbles, 3 green marbles, and 4 orange marbles. If the event is picking a red marble, notice that there are 2 red marbles that are in the bag. The complement of red are all the marbles that are not red, are the non-red marbles. And there is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 non-red marbles in the bag. That must mean that there is 10 marbles total. Let's check. 1 blue plus 2 red plus 3 green plus 4 orange equals 10. The number of red, which is 2, the number of non-red, which is 8, when added together equal 10, the total number of marbles in our bag. The event of picking a blue marble. There is 1 blue marble in our bag. So the complement of blue is not blue. There is 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 non-blue marbles in our bag. Notice that 1 plus 9 is 10, the total number of marbles in the bag. The event of picking an orange marble. There are 4 orange marbles in our bag. The complement of orange is not orange. There is 1, 2, 3, 4, 5, 6. There are 6 marbles that are not orange. Notice again, 4 plus 6 is 10, the total number of marbles in our bag. The Titanic mortality table. We're going to use this table to answer probability questions. The event of picking a man. Well, there's 1,692 men aboard the Titanic. The complement of men are all the non-men. It's everyone else. The girls, the boys, and the women. There's 531 non-men. Notice that 1,692 plus 531 is 2,223. The event of picking a survivor. There are 706 survivors aboard the Titanic. The complement of surviving is not surviving. Notice that there's 1,517 non-survivors aboard the Titanic, in which we add to the 706 equals the total number of possible people on the Titanic, which is 2,223. Total number of passengers. What does this have to do with probability? Well, if we take the complement rule for counting, that first line, n of e plus n of not e equals n of s, and we use algebra and divide both sides by n of s, that's occurring on the second line. Notice that n of s is dividing both terms, n of e and n of not e. That's on the third line. But on the right side on the third line, n of s divided by n of s is 1, because any number divided by itself is 1. So if we take a closer look at that third line, we'll notice a few definitions. N of E over N of S is the probability of E. And N of not E over N of S is the probability of the complement of E. So that what you see on the last line, the probability of E plus the probability of its complement, that equals 1. We're going to use this relationship to answer probability questions. By the way, this is called the complement rule for probability. The following equations are equivalent. The complement rule for probability, I can deduce a second equation. If I subtract P of E from both sides, P of E cancels on the left, but it doesn't on the right. So that we now have the probability of not E is 1 minus the probability of E. I could have taken the complement rule for probability and have subtracted the probability of E from both sides. In which case, on the left, we have cancellation, but on the right, we do not. P of E is 1 minus the probability of the complement of E. We're going to be using this relationship quite often in the future, so I suggest you get used to using it. For example, if you roll a die, what's the probability that the die lands on a first question, a non-5? Second question, a number that's not more than 5. Third question, a non-even number. Notice that each of these events are complements of another event. You pick a card from a standard deck. What's the probability that you pick a card that is 1. Not an ace, 2. Not a spade, 3. Not an ace of spades, and 4. Not a card greater than a 4. Notice once again, all of these examples are complements of events. We're now going to look at a bag of marbles. What's the probability of selecting a 1. Non-red marble, 2. Non-blue marble, and 3. Non-orange marble? Notice again, all of these are complements of some other events. A bin contains 2,000 DVDs in which 250 are defective. What's the probability of picking a DVD that is 1, not defective? Back to the Titanic mortality table. Once again, we're going to be using information from this table to answer probability questions. If you pick a passenger at random aboard the Titanic, what's the probability of picking a passenger that's 1, not a man, 2, a non-survivor? Definition of the odds for an event. That is N of E to N of not E. This is the ratio of the number of outcomes in the event to the number of outcomes that are not in the event. This is also thought of as the number of successes to the number of failures for an event. The definition of the odds against an event E. That is the ratio of n of not E to n of E. It's the number of outcomes that are not in E to the number of outcomes that are in E. This is also thought of as the number of failures to the number of successes. When you roll a die, what's the odds for rolling a 5? 2. Rolling a number more than 5. And 3. Rolling an even number. When you pick a card from a standard deck, what's the odds for picking a 1? Ace. 2. Spade. 3. Ace of spades. 4. A card greater than a 4. When you pick a marble from a bag of marbles, what's the odds for picking a 1? Red marble. 2. Blue marble. 3. Orange marble. A bin contains 2,000 DVDs in which 250 are defective. What's the odds for picking a DVD that is defective? The definition of the union of two sets A and B. That is a list of items that are in A or B. This is often thought of as taking two sets and marrying the two sets, putting them together, joining them, forming the union. The definition of the intersection of two sets A and B. That's the list of items that are in both A and B. The intersection is often thought of as where two sets intersect, where they meet, where they overlap, or which items are in both sets A and B. For example, if a couple were to get married, the husband brings a list of items with him to the marriage, and the wife brings some items as well to the marriage. So on the left, the husband has brought a TV, a couch, his PlayStation, his refrigerator, his dog, a bed, and he brought his mother to the marriage. The wife brought a radio. She brought a couch. She brought a computer, a refrigerator, her cat, another bed, and she also brought her father to the marriage. Notice that the husband brought 7 items, and the wife also brought 7 items. The union of those two lists, those two sets, is found by taking everything that the husband owned and adding everything that the wife owned to the list. This is a single list. This is forming the union. So initially you'll see all of the husband's items, the TV, the couch, the PlayStation, refrigerator, dog, bed, and mother. And now you're going to see the wife's items, her radio, her couch, the computer, her refrigerator, her cat, her bed, and her father. We form the union. However, if you take a closer look, there are 3 items that are redundant. 3 items that they can remove from this list because they have another couch, they have another refrigerator, and they have another bed. So we're going to remove the items that were listed on both sets. This is the true union of list H and list W. The items that are redundant, the items that are highlighted in red, those items are on both lists, so that means that those items are on the intersection of H with W. Here, there are 11 items that are on the union of H and W, if we exclude the items that were redundant, which we have to. The intersection, which of course was the couch, the refrigerator, and the bed. This was the list of items that were on both lists. And there are three. There are three items in the intersection. If we take a look at two other lists, maybe grocery lists, the husband writes down the list of items he wants at the grocery store: steak, potatoes, beer, water, oranges, pineapple, bread, and cereal. The wife requests vegetables, water, milk, bread, fish, cereal, chicken, and tortillas. Notice when we combine these lists, we form the union. There may be some items that are in both lists. The husband wants 8 items. The wife wanted 8 items. Let's take a look at what happens. Water, bread, cereal, and beer were listed on both grocery lists. So what we do then is we simply remove one set of water, one bread, one cereal, one beer request. Notice that we're still going to buy water, bread, cereal, and beer. We're just not going to purchase it twice. The items in red are in the intersection. However, the true union has 12 outcomes, or 12 items, 12 groceries: steak, potatoes, beer, water, oranges, pineapple, bread, cereal, vegetables, milk, fish, and tortillas. The intersection were the 4 things that were redundant. Water, bread, cereal, and beer were listed on both lists. They were listed twice. Take a look at a Christmas situation. The husband and wife both make lists of people in which they like to give presents to on Christmas. The husband has Bob, Ann, Eddie, Larry, and Stephen. The wife lists her friends, which may include the husband's, but she wrote down Melanie, David, Raheem, Dawit, and Richard. The husband happened to have 5 friends. The wife had 5 friends. When they combine their Christmas lists together, let's see what happens. When they form the union, they have Bob, Ann, Eddie, Larry, Stephen, Melanie, David, Raheem, Dawit, and Richard. Notice that there are 10 people on this list. Can you see anyone that was listed twice? Can you see anyone that was on both lists? The intersection of the two lists, or the two sets, are empty. There is not a single person that was listed on both lists. This is the symbol for the empty set, or the empty list. Notice that there is no items, or 0 items, on the empty set. And this is actually the definition of 0. The addition rule for counting n of a or b is n of a plus n of b minus n of a and b. Take a look at this Venn diagram. The people in silver are either in A or B. They're either in region A or region B. If we wanted to count these people, the number of people that are in either A or B. We can do this as follows. We can count everyone that's in region A. And so we'll notice that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 people in region A. We can then now count everybody that's in region B. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 people in region B. Do you notice any problems with this method of counting everyone in A and then counting everybody in B? Yes, the people that are in both region A and B, the 3 people, they were counted twice. This is the very reason that we throw them out once. That's minus n of A and B, because they were counted twice. What does this have to do with probability? Once again from algebra, if I take the addition rule for counting and I divide both sides by n of s, on the right hand side, n of s is dividing all 3 of those terms. So if I look at line 2, n of a is divided by n of s, so is n of b, and so is n of a and b. And if we take a closer look at all of this, we'll notice the definition of probabilities. That is, n of a or b divided by n of s is the probability of a or b. N of a divided by n of s is the probability of a. N of b divided by n of s is the probability of b. And n of a and b over n of s is the probability of a and b. We're going to use this formula to answer probability questions. This is known as the addition rule for probability. That is, if we ever have to answer a question regarding probability of an A or a B event, we will use this formula. We're going to pick a marble from a bag of marbles. What's the probability of picking a question 1? Red and blue marble. Question 2. Red or blue marble. We're going to pick a card from a standard deck. What's the probability of picking a 1. Ace and spade. 2. Ace or spade. 3. Club and diamond. 4. Club or diamond. The Titanic mortality table. We're going to use this table to answer probability questions. If you pick a passenger at random, what's the probability of picking a passenger that's 1. A man, 2. A survivor, 3. A man and a survivor, 4. A man or a survivor? Definition of conditional probability. That's the probability of A given that B has occurred, or the condition B has happened. That's defined to be n of A and B divided by n of B. This is a very useful definition to compare various groups of people. For example, if we pick a passenger at random, what's the probability of picking a 1. Survivor, given that the passenger was a man? 2. Survivor, given that the passenger was a woman? So notice in question 1, the condition, or what's occurred, or is what is known, is that we're dealing with men. Using the definition, we're really determining, of all the men, what was the likelihood of surviving being a male. In question 2, the condition that comes after the phrase given that is that the passenger was a woman. So looking at the definition, we're considering of all the women, what was the likelihood that a woman survived? Let's take a look at the table. If we look at the survivor row and the men column, we're going to find that there were 332 men who survived aboard the Titanic. Out of the 1,692 men, we're going to divide these two numbers. Back to the table. If we take the survivor row with the women column, we'll discover that 318 women survived the disaster of the Titanic out of the 422 women who were aboard the Titanic. We're going to divide these numbers. This is a mortality table in which everyone represented here has died due to a particular cause. Records were kept on both men and women and the cause of death, cancer, heart attack, or by some other means. We're going to use this table to answer probability questions. If a person is selected at random, what's the probability that the person 1 died of cancer, given that the person was a man? 2 died of cancer, given that the person was a woman? And 3 simply died of cancer, irregardless of their sex. If we take the cancer column and the men row, we'll discover that 48 men died of cancer. However, there was 220 men represented in this table, so we're going to use those two values, 48 divided by 220, to determine the conditional probability. We're going to use the cancer column and the woman row. And we're going to discover that 36 women died of cancer out of the 150 women that are represented in this table. So 36 divided by 150 will determine the conditional probability. This time we're going to determine the likelihood of simply dying of cancer. Notice that 84 people died of cancer out of 370 different people that were represented in this table. So 84 divided by 370 is going to give us the answer that we are seeking for question 3.